Okay, I think we're live now. Okay, hello everyone, and welcome to another Talk in a Webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today we have the honor of having Dr. Elisa Alessi, a research scientist at the Institute for Applied Mathematics and Information Technologies. Dr. Alessi's research focuses on astrodynamics problems by means of dynamical system tools, perturbation theory, and numerical methods. Some of her main lines of investigation are space debris dynamics, with special emphasis on passive end-of-life solutions and long-term sustainability, low energy orbits for the exploration of planet-satellite systems, dynamical modeling of solar radiation pressure effect for orbit design, and third body effect for natural and artificial bodies. Dr. Alessi, thank you so much for being so kind and having accepted to give us a webinar talk today on such exciting topics. The floor is yours.
Thank you. Thank you for the invitation. It's my honor. So I have prepared an hybrid presentation I was mentioning. It will be more general at the beginning, and then I will go a bit into the details of my investigation. So I will share the screen. Okay. Okay, so I will start from actually a very nice video that was made by the European Space Agency. Sorry if you can see it. No, just a moment. That can give you the idea of what I'm going to talk about. It's about 10 minutes.
Welcome to a journey of a different kind, one which brings us back to Earth. The objects we encounter along the way are man-made. Originally designed to explore the universe, these are now a challenge for modern spaceflight. We passed Pioneer 10 on its way to interstellar space. Now defunct, it has provided us with fundamental insights into our solar system. Space debris is not a concern out here, so let's rush on. Our gas planets have seen probes flying by. Only Jupiter and Saturn have had orbiting satellites. To prevent contaminating the planet's environment with terrestrial forms of life, they are safely disposed of. We are entering the region of the rocky planets. Besides Earth, Mars is the most observed. We can track the location of active probes orbiting the red planets, but not of their inactive predecessors. These uncontrolled spacecraft could become a risk to other missions. Before we enter our home planet's zone of influence, we pass by the so-called Earth-Sun Lagrange points. Here, a balance between forces allows spacecraft to move synchronously with Earth. Despite growing demand for the Lagrange points, especially for space telescopes, there is no risk of congestion. The balance of forces is only perfect to precisely one spot, and the slightest deviation will cause the objects to drift away. To prevent a return to Earth, ESA's former Herschel and Planck space telescopes have used their remaining fuel to bring them into an orbit around the Sun. The risk of a return is now close to zero. The next objects we encounter are on highly eccentric orbits, reaching from a few thousand to more than 100,000 kilometers altitude. These orbits are very sensitive to perturbing forces caused by the Sun and the Moon. To prevent long-term interference with frequently used regions due to drifting and uncontrolled re-entry, ESA has modified the orbits of active missions such as Cluster 2 and Integral. The satellites will now re-enter within the next 25 years at safe latitudes. Let's continue and visit one of the most congested regions in space, the geostationary ring. This is the only orbit on which satellites move synchronously with Earth, an ideal choice for meteorological and telecom satellites. The average distance between two objects here is only 190 kilometers. Defunct spacecraft in geostationary orbit can drift and endanger satellites in their vicinity. This is why experts recommend to retire these objects at least 300 kilometers higher to a so-called graveyard orbit, with a successful longer interfere with the geostationary orbit. But can this be guaranteed for all times? Aging satellites are known to release debris, and explosion can occur due to residual energy sources. The resulting fragments can be thrown back and cross the geostationary orbit. The release of residual energy, once the nominal mission is completed, is therefore fundamental. Launcher stages used to deliver spacecraft into the geostationary ring often remain on their transfer orbit and could interfere with active missions. Consequently, debris mitigation guidelines foresee that these stages should be maneuvered out of the geostationary ring and other frequently used regions. Further along, we pass through the region used by constellations for satellite navigation. Like layers of an onion, 4 different constellations make use of 4 different altitudes. Inside these layers, we also find defunct satellites and upper stages. Stable graveyard orbits are difficult to find here. Fortunately, no explosive breakups have taken place so far. As we move even closer to Earth, we see that the number of objects around us is growing. This is the region of the low Earth orbits. 2/3 of all large man-made objects are concentrated here. About 600 active satellites provide us with science and Earth data and telecommunications. They are surrounded by thousands of defunct satellites, rocket stages, and fragments. Plus, this area is facing a surge in spaceflight activity. Smaller and more cost-effective satellites are increasingly launched to low Earth orbit. The only chance to ensure the future use of these orbits is to strictly apply debris mitigation measures. The first is to monitor the environment while spacecraft are still active. ESA satellites like Cryosat-2 have to perform 1 to 2 maneuvers per year to avoid collisions. The second measure to combat the harsh rigors of years in space is to release onboard energy by depleting fuel, venting pressure tanks, and discharging batteries. Finally, the longer spacecraft stay in orbit, the higher the risk of collisions becomes. Experts fear that one day, a cascading effect of collisions and follow-on collisions might set in making spaceflight in this orbit extremely difficult. A maximum of 25 years in orbit after mission completion is thus recommended. This can be achieved by moving the spacecraft downwards into the denser layer of Earth's atmosphere. In 2011, ESA successfully conducted such a disposal maneuver with ERS-2, lowering it from an operational altitude of 800 kilometers to 600 kilometers, where the remaining fuel was burned. Instead of otherwise 200 years, ERS-2 will now re-enter in less than 10. On their way down, objects pass through the altitude of another man-made object, our human outpost in space, the International Space Station. Although the environment here is relatively clean, it is not risk-free, as shown by the many impact chips on its surface and the regularly conducted collision avoidance maneuvers. In even lower altitude, uncontrolled objects are bound for a re-entry. To minimize risk, larger spacecraft must be brought down using a complex, controlled maneuver to a selected safe spot on Earth. Without such a maneuver, the time and location of re-entry are not under control. The uncontrolled re-entry will start after a final orbit revolution at about 100 kilometers. First, the aerodynamic forces will cause the exposed external parts of the spacecraft to be sheared off. During deceleration, the object will be exposed to extreme heat. Some materials, such as aluminium, will begin to melt. The outer shell is gradually destroyed. Internal elements are released to the airflow and dissolve. In addition, strong aerodynamic deceleration enhances the destruction process. With complete disintegration, only components made of heat-resistant material, like titanium or glass, will have survived. They cool down and fall with a terminal velocity of about 300 kilometers per hour, mostly into the vast seas. Occasions to find space debris objects on the ground are very rare, and unlike meteoroids, they do not form craters. We have reached the end of our journey. Spaceflight has put mankind forward in the endeavour to understand our universe. It provides us with unique insights into our home planet and makes us aware of our responsibilities towards it. To ensure future exploration and exploitation of space, we need to tackle the challenge of space debris. The countermeasures described in this film are a first step. With joint and continuous efforts of all spacefaring nations, we will be able to achieve this goal.
Okay, so this video, I hope that has given you the idea of the problem, and then here now I will give you some more details. So how many satellites are orbiting the Earth? So before the advent of the large constellations in the past 2 or 3 years, we have launched about 6,000 satellites, and now there are about 1,000 satellites that are currently operational, plus 3,000 additional ones that have been put in orbit by Starlink for the the Starlink constellation by SpaceX. So if you can see from these plots that the evolution of this launch traffic as a function of the mass of the satellites on the left, and on the right the purpose of these satellites. These are mainly in LEO. That well, the video already told you, but I will tell you later also. That is the low Earth orbit region up to 2,000 kilometers of altitude. So you can notice that at the beginning we had many massive spacecraft, like big ones, the yellow bars. While now we are launching like less massive satellites, thanks to the new technology that ensure to miniaturize all the whole system. On the right, you can notice instead the purpose of these satellites. At the beginning, they were mainly defense satellites or for civil purposes, while now there are mainly for actually Earth observation, but also for commercial uses. So, but how many are the debris? The debris are the non-functional satellites, the intact ones, but also the pieces of satellites that are the consequence of mainly breakup, collisions, or deliberate fragmentations. In total, we have the estimates is what we can observe, that is track about 30,000 objects that are larger than 10 centimeters. Depending on the altitude of these satellites, that is how far they are from the surface of the Earth. In LEO, we can track objects up to starting from 10 centimeters, while in GEO, starting from 1 meter. But then we have statistical models that are based on dynamical models, but also on the actual measurements. For instance, on the ISS or on the Hubble telescope, and so we can estimate how many fragments we have that are with the size lower than 10 centimeters. So the current estimate say that we have more than 1 million from 1 to 10 centimeters and billions of a lower size. Even if these are small pieces, the collision can cause an operational satellite to break up and to generate more fragments, because you have to think that these satellites and these fragments travel at a speed of about, well, in LEO 7 kilometers per second. So the collision would release a very large amount of energy. So as I was saying, the main let's say responsible for the creation of the debris were the breakup. That is, at the beginning, the spacecraft were left in orbit with all the propellant on board. So at a certain point, they exploded. We had collisions, and we also now we are having collisions between a fragment and an operational satellite if it cannot maneuver, or a fragment and an operational satellite. The most maybe the first important one was this between the Cosmos 221 first and Iridium 33 in 2009. But then we have also the deliberate fragmentations that are mainly anti-satellite test. That is, the first one was in 2007. Here on the right, you can see the evolution of the space debris in the tracked ones as a function of time, and the color tells you the type, that is if it is a rocket body, a payload, or other type of object. So you can see that the number is increasing, and that we have like a jump at about in 2007, and this was due to the famous, let's say, Fengyu 1C anti-satellite test performed by Chinese, that they deliberate hit one of the satellites to test a technology for let's say for a future war. So in general, the situation is that the number of debris is increasing, and we cannot really stop this growth. But what we can do, we can control this growth, and there are different aspects that concur to this. So so first of all, we have to see these objects, to observe them. The observation and the estimate of the state shall be accurate, and we have to assign every observation to a given object, so that we can monitor its evolution and see how he will move and if will cause a risk to other satellites. We have the part of the modeling, that is the long-term evolution models, the statistical ones that I was mentioning before. We have the operational part, that is the collision avoidance procedure. So for actually continuously we have to pay attention if two objects have a probability of collision less than a given threshold, and in this case one of them they should communicate and decide to move to avoid the collision. Then we have the end disposal, then the life disposal. That is actually my field. That is when the satellite has ended its operational life, that is the scientific mission or the commercial one. We cannot just leave the satellite where it is, but we should dispose it, move it on a region where it cannot cause any risk to other satellites. Depending on the altitude, actually two kind of disposal. A disposal toward a so-called graveyard orbit, that is an orbit where that is usually not used for scientific or commercial purposes, or a re-entry. That is, we should guide the satellite towards the atmosphere, where it can actually re-enter into the Earth and burning. Even if this re-entry, actually I'm very fan of this disposal, but with the re-entry assessment is a very complex task, because not only we have to find the right way to achieve the re-entry, but also we have to control where it will re-enter, and also that be sure that it will burn completely. That is not always the case, because it depends on the material of the given of the systems. For instance, titanium that has a high temperature, melting temperature, we can find tanks on Earth, as seen in the video. Then we have the protection, that is on the satellites. We should put proper shields so that if a fragment collides, it will not, well, a small fragment, it will not harm it seriously. And then we have the regulations. The well-known mitigation guidelines that are international agreements but not binding, that recommend what we have to do at the end of life. In particular, we have two protected regions for which we have end-of-life disposal guidelines, but also we have to passivate the spacecraft. For instance, that is we have to switch off all the batteries and remove all the propellant on board to prevent from explosion. And then we have the two other tasks that are the active debris removal, that still is under study. That is, can we go there and remove one intact object, very massive, that is not operational, so that we remove the risk to create fragments from that large object. Who will pay for that? What are the international agreements? So it's just not a matter of technology, but it's also a matter of political aspects. And the same can be said about the space traffic management that actually comprises many of these aspects that I was mentioning before, in the sense that we have to improve the accuracy of the observation. We have to push the operators to be more compliant with the regulations. We have to decide who will maneuver in case of a high risk of collision. And this is also an aspect that the international community is taking very seriously. Now a bit on what an orbit is, a very general slide here, because this is actually my field. So maybe you already know it, but an orbit around a given planet, or actually massive body in general, is defined by 6 orbital elements that define the size, in particular the semi-major axis here, A. The shape, that is, the orbit can be only a conic section, but it can be so an ellipse or a parabola or an hyperbola. This depends on the energy of the orbit with respect of the energy of the particle, let's say of the satellite or the asteroid or the moon around the given the central body. But according to the eccentricity, we can say, for instance, that the ellipse is more or less eccentric, that is less circular. And then we have 3 parameters that define the orientation of the orbit. The inclination, that is the inclination with respect to the orbital plane, is not usually the reference plane. The reference plane is usually the equatorial plane of the Earth, or the ecliptic plane, that is the plane where the Earth orbits the Sun. And we have 2 additional ones that are the longitude of the ascending node, big omega, that is the angles where the 2 planes intersect, and the argument of pericenter, the small omega, that is the angle associated with the closest point to the the central body for us is the Earth. And then we have a last orbital element, that is theta. Well, that is an anomaly. That can be the true anomaly, or the eccentric anomaly, or the mean anomaly, that defines where the spacecraft is on the orbit. So this is important to understand the orbital regions. So actually, the main orbital regions around the Earth are these four types. We have the low Earth orbit, that is actually a spherical shell around the Earth of an altitude of about 2,000 kilometers. And this is the most crowded region around the Earth, where we have all the mainly the Earth observations satellites, but also the large constellation ones. Then we have the geostationary orbit, that is defined by a condition of synchronicity with the period of rotation of the Earth. It is at this altitude of 35,000 kilometers, and it is important for telecommunication purposes, because a satellite put there, as seen from the Earth, it does not change its location. And these are the 2 protected regions, because you can see here on the same figure as before, that most of the satellites are in LEO, that is the blue bar, and in GEO. The GEO is here is the red, the light blue, and the yellow, the yellow bar. So since these are the most exploited regions, they are considered protected. So we have very specific indication on what to do at the end of life. Then we have other two regions that are the medium Earth orbit between the LEO altitude and the GEO altitude. And this is known because the navigation satellites, that is Galileo, GPS, Beidou, and GLONASS are located. And then we have highly elliptical orbits that are orbits that have the general definition to be very eccentric. So actually they cross all the three regions in general, LEO, MEO, and GEO, and that are usually used for astrophysics purposes like XMM or integral. What is the official recommendation for the LEO region? Is that the space systems operating in LEO shall be disposed of by re-entry into the Earth atmosphere within 25 years after the end of the operational phase. So the idea is that the altitude is low enough to get to the atmosphere, and then the atmosphere will help the satellite to re-enter. I will give you a bit more details on that in the following, but I want you to see these plots where also from the European Space Agency, where we can see the number of operators that actually have comply with these guidelines. In particular, on the right, that is the payload's clearance in low Earth orbit, that is the satellite, not the rocket body. So you can see that a high percentage, it is increasing, it is decreasing, but it's still high. Did not even attempt to do this. This is the light blue bar on the right. You can see that we have a compliance of about 60%, but still this is not enough. And why is that? Because for the operators is less expensive in terms of delta V, that is propellant on board, to put the satellite on a graveyard orbit above the protected region, that is above 2,000 kilometers, rather than dispose it into the drag regime. But this is a problem because if we accumulate a lot of uncontrolled spacecraft in a region of space that is somehow, yes, not very broad, and all these satellites are not operational, that is, they cannot maneuver in case of a risk of a collision, this will create eventually a lot of fragments. So in the past year, I have worked a lot on seeing if we can help these operators to facilitate the re-entry. So if they don't have a lot of delta V budget, we say, that is a propellant on board, can we exploit some physical effects, that is a natural perturbation on the orbit, to make this disposal more convenient? So the idea is that as a first approximation, the orbit of a satellite is modeled by a two-body problem. That is, we have the satellite that is orbiting the Earth, just two bodies. So the satellite is accelerated, is attracted by the gravitational acceleration of the Earth, and it moves, as I was saying before, on a conic section. So generally, since the energy is negative, in an eccentric or circular orbit around the Earth. The orbital elements are constant. So as a first approximation, we can say the size is always the same, the orientation is always the same. So how can we move the satellites toward the Earth? Luckily, it's not so easy in the sense that we don't have just the Earth, and the Earth is not a perfect sphere, but we have other effects. So we have the fact that the Earth is not a perfect sphere, so it is oblate. It has let's say a pear shape and the zonal harmonics, the tessera harmonic, etc. But then we have the fact that apart from the Earth, we have the Moon and the Sun that also exert a gravitational acceleration on the satellite. We have the atmospheric drag, that is the atmosphere exerts a drag up to about 800 kilometers from the Earth, and its effect is to circularize the orbit, that is to make it more circular and to shrink the semi-major axis. So this is why in Leo we can recommend an end-of-life disposal towards the Earth in less than 25 years. But if we are not actually below 600 kilometers, that is the time that the altitude where we can naturally re-entry just thanks to the atmospheric drag in 25 years. Is there any other effect that can help us in shrinking the semi-major axis, that is the orbit, or enlarge the eccentricity? Because if we enlarge the eccentricity, it means that the closest point to the Earth, the pericenter, gets closer, given that the semi-major axis does not change. So to do that, we have to analyze all these effects, so the dead body effects, that is the acceleration of the Moon and the Sun, or the geopotential, the solar radiation pressure, according to the time scale and their effect on the given orbital elements. It turns out that the geopotential in the long term, if we consider the most important term, that is the J2, the fact that the Earth is oblate, it makes the argument of pericenter and longitude of the ascending node to vary. That is, it changes the orientation of the orbit, but not the size or the shape. If we consider further a higher order and consider also the tesseral harmonics, their effect is mainly in the semi-major axis that undergo a periodic oscillation, but not enough to re-enter towards the atmosphere. But if we consider the Moon and the Sun, that you can see that in Mio can become more significant, or if we consider the solar radiation pressure, given that we assume a high area to mass ratio, then we can think to increase naturally the eccentricity, because both the third body perturbation and the solar radiation pressure in the long term, they make the eccentricity to increase. So this is the main idea that I've used in my investigations in the past. I will focus now on the role of the solar radiation pressure in Leo, but similar ideas can be considered also for the third body perturbation in Mio. So, as I was saying, solar radiation pressure in LEO, we have the photons that hit the spacecraft, and they exchange linear momentum. On the right, instead, we have the case of the lunar solar perturbation. So the spacecraft is accelerated also by the sun and the moon. The maximum effect of both perturbations turns out to occur at an orbital resonance. In this particular configuration, we can leverage the instability of the orbit and drive the spacecraft towards the Earth. So, so in the case of the solar radiation pressure, it is actually the couple effect of the solar radiation pressure and the Earth oblateness. So we assume that we can embed the spacecraft with a large enough solar sail so that we can exploit the momentum given by the photons to increase the eccentricity. But at the same time, we need also the Earth oblateness because the resonance is mainly due to let's say, commensurability between the angular orbital elements, the 2 omegas, and the position of the sun at a given time. And the main variation of these orbital elements is given by the Earth oblateness. So for this passive deorbiting solution, we exploit on one side an advanced technology that is a solar sail, but on the other hand, we have a very, let's say, advanced or accurate astrodynamics analysis that is based on a complete analytical formulation based on a simplified model, but it is then actually later confirmed by numerical simulations. These orbital resonances are what we call the natural deorbiting corridors enabled by a solar sail and a resonant condition. So here I go a bit into the details, but not many formula. So the simplified model assumes that the spacecraft is always in starlight, that is, we don't have eclipses. And also a cannonball model, that is the sun is the surface of the spacecraft always perpendicularly. In this way, we can assume that the dynamics is driven by this Hamiltonian function that is composed by one Keplerian part, that is the two-body problem, that is the constant ellipse, plus a perturbation. And the perturbation is composed by the oblateness effect, that is J2, and the solar radiation pressure. There are some simplification on this Hamiltonian. In particular, we consider the long-term dynamics. That is, we don't care about the effects on an orbital period of a spacecraft that is about in 1 hour, but we want to see what happens in years or months. And in this way, we can conclude that the only variation associated with these two effects are a variation in eccentricity and a variation on a given angle C. Here you can notice in particular that the variation in eccentricity is proportional to the sign of C. So if the argument of psi is almost constant, we have the steepest variation in eccentricity. And the steepest variation occurs if we are at a resonance, that is, if the second equation is equal to 0. So with this idea, we can draw phase spaces. I don't know if you are familiar with phase spaces, but essentially we can depict the dynamics on a plane with the two most meaningful variables. and we can see the corresponding variation, mainly associated to equilibrium points that are the red points. So how I can dispose my spacecraft? I can dispose my spacecraft. I would like to have a pointer, but I don't have it. Okay, but if maybe you can see if you start from a almost circular orbit that is eccentricity almost zero, that is the most usual common case for a satellite in LEO. I want the eccentricity to be to become larger enough to touch the well, not touch the Earth, but touch the atmosphere. So this means that, for instance, on the plot in the figure in the middle, if I start from an eccentricity almost equal to zero and an angle that is about 90 degrees, I have that curve that is like a mountain that can reach an eccentricity of about 0.3. So this is a natural effect. I haven't applied any maneuver. I am just on the right resonant condition. The other point to consider, so these are the orbiting corridors in for a quasi circular orbit that is eccentricity almost zero as a function of the inclination of the orbit and the semi-major axis. We have 6 possible resonances, and the commensurability of the variation can be computed analytically as a function of the semi-major axis, inclination, and eccentricity. So you can see that why we call them corridors, because it's not that in every point for every orbit we can exploit them. It's just if they are close to these values of inclination and semi-major axis. As a matter of fact, it's important that they are close to these values of inclination, because in general it's very expensive to move the spacecraft its orbital plane. And from a technological point of view, and also from the guideline point of view, how big should be this sail? And if can I orbit in less than 25 years following these routes? So I didn't tell you before, but if you look to this formula, the variation in eccentricity proportional to the constant c, that is that includes the area to mass ratio, that is the area exposed to the solar radiation pressure and the mass of the satellite. So the larger the area to mass ratio, the larger the effect. And there exists a minimum for which we can actually exploit the solar radiation pressure. If we combine the current technology that is that can ensure an area to mass ratio up to 3 to 5, let's say, meters square per kilogram, we can actually deorbit from an altitude, from a semi-major axis of about 10,000 kilometers. That is, since the radius of the Earth is about 6,000 kilometers, it's an altitude of 4,000 kilometers. It is very high because it's higher than LEO. Both for corridor 1 and corridor 2. So we have to be close to 40 degrees or 80 degrees. But we can exploit also resonance 3 and resonance 4. And in this following these corridors, on the right we can see the solid circles say which area to mass ratio we need to deorbit in less than 25 years. So at least we need 1 meter square per kilogram, or even a bit more. So this is the analytical part. Then with on the left we have the corridors depicted with the with the analytical model. The color bar depicts the maximum variation in eccentricity, while on the right we have the same corridors, but that were obtained with a full model that is not only considering J2 and solar radiation pressure, but also the atmospheric drag, the geopotential, and the turbidity effect. So we can see that the color bar in this case depicts the lifetime in years. So if it's yellow, it means that it is okay. So we can see that they actually persist, even if we consider a more realistic dynamical model. And finally, we have analyzed this corridor in terms of their effectiveness, that is considering one of this long-term evolution model to see if we actually apply this disposal strategy, that is if we think that we have some propellant on board, but also the possibility to opening a sail, and we are close enough to a corridor, what is the evolution in 200 years of the current population? So the estimate of the effectiveness in this case was done by comparing the possibility of using 100 meters per second for a maneuver to re-enter into the atmosphere, or 20 meters per second for a maneuver to get into the corridor and then open a sail. So you can see, so on the y-axis you have the number of objects and their evolution in 200 years. So you can see that with a sail and a propellant budget 1 order of magnitude less, the number of objects is half of the blue curve. So actually we have a big improvement by considering this strategy. So this is what we did for the solar radiation pressure. We did something similar also for MIO. I will not explain this now, but the idea is similar. That is as a function of the orientation of the spacecraft. We have numerically simulated the maximum eccentricity considering the turbidity effect and the J2 to look for the regions where we can achieve the maximum eccentricity and if this maximum eccentricity can ensure a re-entry. The problem here is more complex from one side because the altitude is much higher. It's the navigation satellites are at about 30,000 kilometers from the Earth. Well, semi-major axis, so 24,000. And also because the resonance here are, there is like a network of resonances. So the interpretation is still ongoing. That is, at the moment, it's still an open problem. That is, if the increase in eccentricity is due to one single resonance, as in the case for the solar radiation pressure, or if it's actually due to chaotic behavior for the fact that we have two or more resonances that overlap. And if it's actually due to chaos and not to a single one, the question is how to target optimally the stable or unstable solutions. So this concludes my presentation, and I want you to receive the message that the dynamical awareness represents a new paradigm in mission planning, and where the whole life cycle of a spacecraft, including disposal, is considered from the very beginning on a design. That is, now when we have to design a mission, we don't have to think only on the payload or on the propellant aboard or on the launch, but also on the mitigation guidelines, and in particular to the end of life phase. And if we can model accurately the dynamics, this will help significantly this phase. So thank you for listening.
Thank you so much, Dr. Alessi, for the very interesting talk. We now have time for questions from the audience.
Well, I would have a question. Let me Otto, if you want to ask first, please go ahead.
Okay, so very nice presentation, Elisa. I have a question about the well, it's what has not been done. How much would the shadow of the Earth affect the time evolution for removal using your approach? You have an idea?
We actually have simulations considering also shadows. What happens is that the corridors that I was showing persist, but there exist other corridors. So other corridors are created, and we didn't actually investigate them yet, but we would like to do that. And for the time, actually, I think that it is not the shadow that is relevant for the time, because it's more the atmospheric drag and the other effects that get the situation, makes the situation more complex, in particular the drag.
Okay, thank you.
Thank you. But actually, this is yes, your question is something that I would like to do in the future to understand the role of the shadow. But it's different, the analysis, because I cannot average over the mean motion of the satellite, so it's not it's different, the analytical part.
Okay.
Thank you.
Rodrigo, you had a question?
Well, yes, it's more a curiosity. Elisa, what is today the perspective? We have so many satellites and swarm satellites being launched. In the near future, how does this affect launching, for instance, something into space? Is this how complicated is it at the moment? This traffic of satellites and debris.
Well, yes, it's complicated in the sense that well, I think that the constellation will not be stopped, because it's something that I think that it's needed for internet access, etc. But to be sustainable, they have to be very, very reliable in terms of failure, in terms of operations, because we have like 100 of satellites going on orbit and be disposed continuously. So if any of them will fail or fragment in low Earth orbit, it will create this disaster. And also for the actually for the launches, for the scientific ones at the moment, I don't think it is a problem of finding the good spot. But for astronomers, I know that there is a problem on for your observations, because they have this big. Actually, I'm not an expert on that, but they contaminate the sky somehow. But for instance, SpaceX is receiving the message, so he has tried to make the satellite more darker, so that they can affect less the observations of the telescopes, and also the attitude of the spacecraft play a role in the sense that how much they reflect the light. But yes, it is certainly a matter of how to manage these constellations and to be sure that you can they can really be compliant with the disposal guidelines, where they can really maneuver to avoid a collision, and the design should be very, very reliable. All these aspects are being considered at the moment.
Well, okay, thanks. I have another question that is regarding to the. I think I probably did not understand, but those satellites that are in higher orbits, are this the disposal maneuvers? Does it work for them as well, or are you studying another type of solution?
Well, no, this solution work only for in LEO. It is a lower orbit. For higher orbits, they are actually considering the dead body perturbation, both for MEO and GEO. Well, in GEO you should be in GEO only if it is an inclined GEO, because you need to have a bit some inclination to exploit the contribution of the sun, and mainly it's the contribution of the moon actually. And for MEO, they are actually I think they are interested, well, at least the European Space Agency is interested in that. And but it's not an official guideline, because well, because it's more complex, because it depends on how long it will take to get back to the Earth. So in MEO, you don't have the guideline that you should re-enter into 25 years, but the idea is that you should your pericenter should get in LEO not more than 25 years. So I don't know if you can explain me. Like since it is an eccentric orbit starting from MEO, at a certain point, the closest point will be in LEO, so at a lower altitude. So we should pay attention that the amount of time spent there will not exceed the 25 years. And also, the problem is that if it will take 60 years or 100 years, can we wait so long? So there are different aspects to be considered, also from the like the operators and who is tracking them, who is monitoring the re-entry, etc.
Okay, well, thanks, and thank you for this awesome talk. It was very interesting.
Thank you for the invitation.
Thank you so much. Do we have any more questions? Or a little bit?
I do have a question.
Go ahead.
Well, first of all, thanks, Elisa, for your talk. It was very interesting. This question comes from a very lay person. I do not know that much about the subject, but at the beginning of our talk, you mentioned something about keep track of the satellite debris. And I was just wondering how to do it. I mean, is it just a matter of knowing where the bodies who generated this debris was, I mean, where the orbit was, and then modeling where these debris orbits are now, or do we observe them somehow? I mean, do we actually observe this debris somehow?
Well, there is an official network that is devoted only to observe debris. That is the US Stratcom. It is a US official service. It is made of 25 observatories, and it is both radar and optical. Depending on the altitude, they want to keep track of the objects. But actually, they look into the sky looking for these objects. And so in some cases, they know where to look because they know that the fragmentation has just occurred, or they know the catalog. So every piece of the catalog shall be monitored in time. So, but in other cases, they will find other new pieces.
Yeah.
Does this answer to your question? I'm not really an expert on this part, but the idea is that we need an ad hoc network just for debris.
Yeah,
like we have one for asteroids, for NEO, or one for, I don't know, your scientific purposes. Also for debris, we need one. And also in Europe, we have one, but at the moment, well, I think the reference is the US one.
Yeah, I see. I mean, I was thinking that it was just a matter of simulation. So there are actually surveys looking for these debris on orbit, right?
Yes. Actually, it's fundamental to have it. For the collision avoidance, you need to have a real measurements of where they are and the possible collision.
Do we have any other questions? Maybe. Okay, if there are no more questions, we'll wrap this up. This presentation is available on our website and on Linea's YouTube channel. I want to thank everyone for attending, and a very special thanks to you, Dr. Alessi. Everyone, have a great day, stay safe, and I hope to see you all again in our next webinar.
Thank you very much for the invitation, and I hope that you enjoy it.
Very much.